Okay, so just started recording. Let's go ahead and continue with what we were doing last time. So last time we saw the series diode clipper, and this was the negative clipping or negative clipper version of this circuit. And what we saw was for the given input of V in going all the way up and down to a positive and minus 10 volt, so 10 volt peak signal. We saw that we do follow only the positive portion of the waveform, and we always stay at 0.7 volts below whatever the input is. And then once we get to the negative alternation, all of a sudden we're at 0. That diode is not conducting, and so we get no current flowing through it. Okay, so let's go ahead and continue this. The remaining ones I'm not going to do with an ideal diode. We're going to look at it using a 1N4001. Okay, and the 1N4001 is a type of rectifier diode, and its primary purpose, the reason it was created, was primarily for this idea of rectification, where we preserve one side of this sine wave. And we will get to that. There are useful applications for this, especially for power supplies, power circuits. Hence the name rectifier. So let's go ahead. Let's continue on with the next one. The next one, again, is going to be a series diode clipper, but we're going to go ahead and flip the diode around.
Hey, Professor.
Yeah, what's up?
Can you go back to how you got 0.7 volts for VF?
Okay, so 0.7 volts. V sub F is a characteristic. So that is built into the diode. When you select a diode for any circuit, the forward voltage, which is what we use for that second approximation analysis for any of these circuits, is given by the manufacturer. So you would find that inside of the data sheet. So very similar to like in lab, where I did the LED lab and I pulled up the data sheet, the manufacturer data sheet for that specific part, and it told us that approximate, like I believe it was 1.8, or it gave a min and max. So that's actually just that's just part of the diode. And when we get next lecture, or towards the tail end of today's lecture, we're going to get into the kind of just some basics of the semiconductor physics. So how you actually construct a device like a diode. And we'll see what that voltage is in reference to, like where do you get that voltage? Okay, so for right now, just take 0.7 as being given. As we will find out, semiconductors made out of silicon generally have a V sub F about 0.7 volts. There's another material. You could use germanium in order to create a diode, and if it's made out of germanium, you would have a smaller forward voltage of around 0.3 volts, and the LEDs are sort of their own type of component. And forgive me, I don't know what the chemical process is that they use for creating an LED. At least I did at some point, and that's not something I just carry around with me all the time. And LEDs have a higher V sub F. They're usually in like the 1.8 volt range. Okay. And in fact, you know what? I'll go ahead and write that out right now. If your diode is constructed out of silicon, then it's got a forward voltage of around 0.7. At least that's what I'm going to be using for this class. Obviously, if you create some different or weird type of diode, you would have something different. But generally speaking, if it's constructed out of silicon, you're going to get a 0.7 volt forward voltage. If it's out of germanium, 0.3, And if it's out of, if it's an LED, I'll go ahead and just state it at 1.8 volts. And so for silicon, that's like the diode we're currently using, a 1N4001. Then we have some germanium. Those are classified as kind of signal diodes. And these have, a good example would be like the 1N4148. And your LEDs are just your general purpose okay. And so if it's a silicon diode, generally speaking, it's a rectifier diode. And if it's something like a 1N4148, it's referred to as a signal diode. There's hundreds of varieties of different diodes. It's created for different intended purposes. Okay, so just kind of rough guidelines on our different diode options. Okay, so hopefully that answers. Let's go ahead and let's look now at another type of clipper circuit. And what I'm going to do is we'll stick with the same AC voltage source. We're going to just use 10 volts peak for these. And let's go ahead and draw up the circuit. And we care about V out, which we know is the same as the voltage drop across this resistor. And we care about V in. And if you notice, the only thing I've done here is I've taken that diode, I've flipped it the other way. So now during the positive alternation, you would be expecting current to go clockwise. And so it's going in the opposite direction of what this diode would permit. So this diode's going to be reverse biased during the positive alternation and forward biased during the negative alternation. So that is different than our previous circuit. That's just the complete opposite. So let's go ahead and let's draw up what V in would look like. I'll do again 1.5 cycles for showing these. And if you have a question, please just ask away, just key in. I can't see hands being raised or anything. Okay, so this sine wave obviously represents our input voltage. And goes up to 10 volts. And down to minus 10 volts. Okay, and again, we want to go ahead, analyze, figure out what this circuit is doing. So we're going to analyze this and ask ourselves 2 questions. We're going to go, well, what does this do during the positive alternation? During the positive alternation, all applied voltage is positive, therefore the current is only going in one direction. So we know the diode's going to behave one way. And then we ask ourselves, well, once we figure this, what happens during the negative alternation? And during the negative alternation, our polarity flips. We're now always applying a negative voltage. And so we expect current to now go counterclockwise. And so we ask ourselves, well, what's the behavior of the diode in this situation? So what I'll do is I'll use this first schematic to answer the question of what happens during the positive alternation. Now, during the positive alternation, our polarity is such as this, coming from our AC voltage source. So we expect current to go clockwise. And now we can go ahead and ask ourselves, well, how's this diode going to respond to this? How's the diode going to behave in this situation? Well, is it reverse biased or forward biased? Hopefully everyone says reverse biased, right? The current's going in the opposite direction of what this diode would permit. The diode is drawn as a schematic symbol that looks kind of like an arrow that's going in this direction. And if current was going in the same direction, it would say, okay, I'm going to behave as though I'm closed. I'm going to allow the current to go through. However, in this situation, the current's in the opposite direction. It's reverse biased, hence it is going to be not conducting. So to a first approximation, I expect the behavior to be like this all the time. Okay, as long as our applied voltage is in the positive direction, which it is during the positive alternation, I expect this to behave like it's open. If it's open, we get zero current flowing through it. If I have zero current flowing through it, then what's my voltage drop across this resistor? Is it 10? It's 0, right? So check this out. Over here, V sub R is equal to, just use Ohm's law, we have 0 current. Right? So we always get a 0 volt drop across this resistor. However, what's the voltage drop across the diode? Now that is 10 volts at the peak, So if we are at the beginning portion of this waveform, we're applying 1 volt, V sub D would be 1 volt. If we're applying 2 volts, V sub D would be equal to 2 volts, 3 volts, 3 volts, etc. All the way up to our peak voltage of 10 volts. Okay, that's the voltage drop across the diode, not across the resistor. Across the resistor, during this reverse bias situation, we're always going to have 0 amps flowing through it, and so Ohm's law tells us we get 0 volts across it. V out is just an extension of V sub R. They are the same in this circuit. And so V out is going to be equal to 0 volts all the time. Okay, so at this point, if I want to draw what happens during the positive alternation, it's 0. Okay, so that takes care of the positive alternation. Let's now go ahead and ask ourselves what happens during the negative alternation. I'll redraw the circuit right below. So, okay, what happens here? Well, during the negative alternation, the polarity applied by our AC voltage source flips. Plus on the bottom, minus on the top. Now current's going in this direction. Is the diode forward biased or reverse biased? It's forward biased. If it's forward biased, does it behave like a does it behave like a closed switch or an open switch? Well, actually, it behaves like both depending on what that voltage is, right? Not only do we have to apply the polarity in the correct direction to forward bias it, but we also must exceed that forward voltage. And the forward voltage in this case is 0.7. Okay, so now let's go ahead. Let's imagine we're applying a few different voltages here. Okay, so I wrote down 6 voltages. 3 of these are below the forward voltage drop, and 3 of these are above the forward above that forward voltage drop. So okay, what happens when we apply 0.1 volts? Well, when we apply 0.1 volts, we're still forward biased. However, it is not conducting, even though I drew this as though it is. We're below this forward voltage drop, so this is not conducting. If this is not conducting, we are in the exact same situation as we were during the positive alternation, meaning that we have 0 current flowing through the circuit, 0 voltage drop here, all voltage gets dropped across V sub D, and we get 0 volts out. So over here, V out is going to be 0 volts in the case of 0.1 volt. Okay, now we get to 0.3 volts. We're still below the forward voltage. This is still not conducting. Therefore, we still have 0 current flowing through this. We get no voltage drop here, and across the diode, we get a 0.3 volt drop. And therefore, V out should be 0 volts. Okay, 0.5 volts, again, below the forward voltage, 0 current. This diode's not conducting. We get 0 volts. Now we get to 1 volt. Now at 1 volt, something interesting does happen. We have now exceeded the forward voltage. This is behaving like a closed circuit. We do have current flowing through it. And now V sub D is always going to be equal to 0.7 volts. And that means that all remaining voltage gets dropped across this resistor. Once we've exceeded the forward voltage, we always have this 0.7 volt drop across here. So now you go ahead and you look at Kirchhoff's voltage law. And Kirchhoff's voltage law says that all remaining voltage must go across this resistor in this situation. So if we're applying 1 volt and I have a 0.7 volt drop here, V out should be equal to 0.3. And as we increase in voltage, say we go to 5 volts, again, 0.7 volt drop over here. All remaining voltage across this resistor, V out, therefore, is going to be equal to 4.3. And for 10 volts, again, we will stay 0.7 volts below the peak voltage of 10 volts. Therefore, 9.3 volts. Okay, so what does that look like? Well, until V in gets below that 0.7 volt drop, we're going to stay at 0. Once we've exceeded that forward voltage drop, now we're going to begin to follow, and we're going to always maintain 0.7 volts greater than our negative voltage. Okay, and then over here again, we've dipped below that forward voltage, so we're no longer conducting. We have zero current and zero voltage drop across the resistor. And then just as the before, during the positive alternation, we're back to that, and again, we will be not conducting. Okay, so this is what the result looks like. And now we can go ahead and answer the question of, well, this is a series diode clipper circuit. Absolutely, we're clipping something. Are we clipping the negative or are we clipping the positive? Well, we're losing that positive portion of this waveform, so this series diode clipper is positive clipping. Okay? So as long as we just keep in mind how we're approaching this analysis and asking ourselves the right question, how's the polarity being applied? What is the behavior of the diode under that condition? And then you bring in your rules like Kirchhoff's voltage law and Ohm's law in order to answer the rest. Okay? Any questions about this one?
Yeah, what's the use for this?
The use? For me to show you an example in class where the diode is doing something under AC conditions. No, that's a good question. Okay, I don't want to say that this is only academic because it's not. I have come across this tons of times in the workplace. Do I set it up like this? Is this an actual useful circuit implementation that I put in my design? No, I do more advanced things than this. However, this is the simplest version of how I may use a diode. So for the sake of instruction, for the sake of demonstration, this is much easier to understand than say the more advanced circuits that you may work with at the workplace, where this is still happening. It's just there's a lot more stuff going on. So you know, the previous circuit, that negative clipping, that one has a direct translation to a useful circuit that we will probably see next week. So as far as that one, I can give you application of that, you know, very soon. And I can tell you right now, it deals with power supplies. But in this case, I can't really tell you right away, like, oh, this is useful. You will find this in XYZ product or XYZ thing around your house. So unfortunately, I'm going to have to go, this is a little more academic in nature, but this situation does happen all the time in professional products. Okay? Any other questions? Okay, so we can go ahead and move on. Let's see, we now have 33 people in chat. Do me one favor, everyone that is here, just type here into chat. All capitals.
Is it easy to take roll this way?
Mm-hmm, yeah. Okay, so I got everyone typed in here into chat.
You went mute.
What? I went mute? You can't hear me?
I can hear you.
Oh, okay. Thank you. Does the microphone sound good? Am I popping and scratching right now?
No.
Okay, perfect. Okay, give me 1 second to enter this in. Okay. So let's go ahead and continue. Now this is the same type of circuit. However, I think there's a little trap in this one that people fall for. We're going to use the same kind of approach to analyzing it. Oh, I kicked my audio line. And you were blaming me. Or my microphone, I should say. You know, there's so many little quirks with doing this thing online. I can't imagine how some of the older instructors are going along with this. It's got to be hard. Okay, so let's go ahead. Let's look at the next two variations of this circuit. And this is going to be known as the shunt diode clipper. I won't tell you what type of clipping this will be yet. We will set it up very similarly to what we did before. We're going to have an AC voltage source. A V out, a V in. I'll keep this to 10 volts peak. And you know what? For this first one, let's go ahead and do ideal. Okay, so an ideal diode, we're going to only look at the first approximation. And then once we have the first approximation, then we can go in and add that little extra information about the forward voltage being 0.7 volts for this diode. Again, it'll be like a 1N4001 rectifier diode. And this is just going to make things a little easier for now. Let's go ahead, draw up what V-in looks like. Up to positive 10 volts, down to minus 10 volts. V-in. Okay. Again, we're going to go ahead and actually, let me go ahead and say, first off, the word shunt. What does that mean? What the hell does shunt mean? Shunt is a fancy word for parallel. Now, what is in parallel here? Now, here's where we go ahead and kind of go, well, what's in parallel? The diode sure is not in parallel with this resistor. However, if you look at the output is being referenced to down here. V out is being taken between these two terminals that I keep drawing. And if you notice, the diode is in parallel with our output. Hence, the word shunt being a fancy word for parallel, it's a parallel diode clipper. Okay, the other one was series. If you think about series, this diode is in series with our output. Our output is here, and this is in series with our output. So hence why this one's called the series diode clipper, and this one is the parallel diode clipper or the shunt diode clipper because the diode is in parallel with our output. Okay. Now, let's go ahead and what am I going to do here? I'm going to go ahead and ask myself what happens during the positive alternation. Okay, during the positive alternation, positive up here, minus over here, the current's trying to go this way. This is an ideal diode. Is it conducting? Not conducting? Well, it's forward biased. The current's going in the correct direction. Therefore, it's behaving like a closed switch. It's conducting. Okay, I'm gonna redraw this just to emphasize and make sure. Okay, positive alternation. Okay, check this out. What's V out? How many volts do I get for V out? I really need to start up my voice mod app so that I can start playing the Jeopardy music. What's V out for this guy? Regardless if this is 1 volt, 2 volt, 3 volt. Is it 10 volts? Let's put 10 volts over here. The only way we would ever get 10 volts on V out is if we had 10 volts coming in. So let's go ahead and just say, okay, positive voltage. I agree, I is greater than 0 amps. Yeah, it's 0, isn't it? All voltage is dropped across this resistor. V out is directly connected to itself. There's no way this circuit would ever have any voltage between these two terminals. I have a direct connection. I have a wire. By definition of a wire, I have the same voltage at every point across that wire. Now, somebody asked, it acts like a wire, right? Ideally. Yes, ideally. If this is a perfect diode, this should act like a wire. And that's what we said. We said that this is an ideal diode with a forward voltage drop of 0. So when this is conducting, we should have a 0 volt drop across it. So yes, your intuition led you in the correct direction. Okay, so let's go ahead and let's draw for all values of the applied voltage. V out is going to be 0 in all cases. So to answer the question, what does this do during the positive alternation? We get 0 volts the whole time. Okay, let's go ahead, continue with this train of thought over here. And now let's ask ourselves what happens during the negative alternation. Let's see. Yeah, I can draw this on this. Actually, no, just to keep it clean. Let's just redraw this up here. So this is during the negative alternation. Same exact circuit. And now all voltage applied is negative. So the current is this way. Okay. So now the question goes, which way does the current go in? Like this. Now, is the diode reverse or forward biased? Obviously reverse biased. Does it behave like a open switch, closed switch? Well, to a first approximation, which is actually this entire circuit, we are taking V sub F to be equal to 0. It behaves like it is open. Okay. And you know what? Just to highlight this, I can redraw it. Okay, now we can go ahead or give ourselves some test cases. Let's say 1 volt, 5 volts, and 10 volts. Okay, if I have 1 volt applied, how much current do I have flowing through this? I did draw this voltage source incorrectly. I had it with the big side, the positive on the top. However, I just fixed that. I made this side bigger, made that smaller, and I labeled this as positive just to be 100% clear. Okay, and as people have said, I have 0 amps going through this. Yep, all day long. Okay. 0 amps. What's my voltage drop across this resistor if I have 0 amps flowing through it? So, if I have 1 volt applied, what is V out?
Zero.
Guys, 0 amps does not equal 0 volts. Only sometimes does 0 amps equal 0 volts. We gotta break ourselves of that. Everyone's getting stuck on this. Whenever you see 0 amps, tell yourself, maybe 0 volts. Yeah, exactly. We have 1 volt in this case. All right, 5 volts. 5 volts. Yeah. 10 volts. 10 volts. So whatever is applied is whatever we get out, right? And by the way, I want to say I appreciate the person who said 0 volts because I get to make that adamant statement about it. We get too comfortable into thinking, well, if it's this, it must be that. But you really kind of need to look at the circuit and use only that 211 material to answer the question. Okay? I cannot look at these circuits and intuitively just tell you what it is. And I've had people like do that. They show me the waveform. Is this correct? And I'm like, I got no idea. I need to go ahead and work through it. I don't memorize these. I just get comfortable with the basic rules that allow me to arrive at my answer. So, you know, if you're thinking, well, I'll just memorize every single case, it's not the best approach for this stuff. Maybe it helps at first, but really you want to get into that habit of only relying on the 211 information, and that's really why I you know, I try to push that in 211. Like, we just need to know this, because we don't have time to you know, once you get to these more elaborate circuits to sort of go, oh wait, series, I think current's the same at every point, is it? Or is voltage the same? No, voltage is the same for a parallel circuit, right? So those types of things, with enough practice in 211, hopefully we got that. Okay. So we answered what happens during the negative alternation. Whatever is on the input is exactly what we'll get on the output. So let's go back to here. And whatever we get on the input, if we're at -1, we have -1. If we're at -5, we're at -5. If we're at -10, we're at -10. And back up. We get to -5, we're at -5. Cool. Okay, and now we're back to the positive alternation, the same thing as we said before. It's closed, and the voltage between these points is 0. So we're back to 0. Okay, so I feel like this circuit is just slightly trickier because of what happens during that negative alternation. This is the trickiest part of that, and it's not too bad, right? Just be on the lookout for this and that little trap. That's what I was referring to like 20 minutes ago about, yeah, there's a little trap with these shunt circuits. Okay. Man, that was just an ideal diode. We still have to do a real diode. I know, I said diode. Diode. We have to do a real diode. All right, let's hop on it. Okay, we're going to do the same circuit now, but we will take out that fictitious fake diode, that ideal diode that doesn't exist. We'll replace it with a 1N4001, which does exist, and I have several of them right on my desk. Do, 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 do. Okay, now this is a 1N4001 with a nominal V sub F equal to 0.7 volts. V sub S is equal to 10 volts. Don't forget the units for AC. We can specify it as peak, peak to peak, or RMS. I'm using peak to keep things easy. Okay, and now we have the shunt diode clipper. Again, shunt because the diode is in parallel with our output that we are calling V out and our input V in. Okay, let's draw what V in looks like. -10 volts, -10 volts. Okay. Let's go ahead and ask ourselves the question. What happens during the positive alternation? Same thing as before. Okay. This diode should be conducting. It's forward biased. Current will be greater than 0. But only when we've exceeded the forward voltage. So we need to ask ourselves what happens below 0.7 volts, what happens above 0.7 volts. Time to redraw. Okay. Perfectly redrawn. And we got to ask ourselves, let's give some values before 0.7. Let's give ourselves some values after 0.7. Zero 0.1, 0.3, 0.5, 1 volt, 5 volts, and 10 volts. Okay. At 0.1 volts, is this diode open or closed? It's open. Diode's not conducting. Current, therefore, is 0. If we have 0 and this is open, just like previously, the voltage drop is the same as the input because we have a 0 volt drop across this. We have a 0 volt drop across this because of Ohm's law. Zero amps flowing through it. 0 times whatever value R this is going to be equal to a V of 0. Okay, if we're at 0.1 volts over here and we drop 0 volts, we're still at 0.1 volts. I'm just doing KVL here, Kirchhoff's voltage law. Now, you can easily see, if I have 0.1 volts over here, 0 volts over here, this was open, then V out must be equal to 0.0. Did I say 0.0? Must be equal to 0.1. Okay, so it looks like whenever we're below 0.7 volts and this is open, we always have 0 amps running through it. If we always have 0 amps running through it, we always get a 0 volt drop across this resistor. If that's the case, then whatever is on the input is what we get on the output. So whenever we're below 0.7 volts, 0.1, 0.3, 0.5, 0.6, we're going to get the same voltage out. Okay, so that takes care of what happens when we're below the forward voltage. Now what happens when we're above the forward voltage? Well, now the behavior of this diode has changed. It's now conducting. Once we exceed that forward voltage, this guy is now conducting. He's forward biased and conducting. He behaves like a closed switch. All right. If it is a closed switch, what is the voltage between these two terminals? What does V out turn into?
The voltage drop of the diode.
Yeah, awesome, awesome. I was kind of expecting somebody to jump in and go, it's 0. For an ideal diode, it would be 0. But in the case of a real diode, with a V sub F equal to 0.7, we always have a 0.7 volt drop across this when it is conducting. All right, what happens once we go to 1 volt? Once we go to that was sorry, that was for 1 volt. What happens once we get to 5 volts? What is the voltage on V out? 5 volts applied. 0.7 volt drop across here. Well, when we're at 5 volts, I also get 0.7 volts. If I'm at 10 volts, I also get 0.7 volts. So it looks like we follow the applied voltage until we hit that forward voltage. Once we hit the forward voltage, we stay at that forward voltage. So essentially, it looks like we are flatlining at that forward voltage. So during the positive alternation for a real 1N4001 silicon-based rectifier diode with a nominal forward voltage of 0.7 volts, it looks like we flatline at 0.7 volts during the positive alternation. For a shunt diode clipper. Okay, so that's a little different. We haven't seen that before. We didn't see that with the series diode clipper, where you just go up to 0.7 volts and stay there the whole time. Okay, so now we gotta ask what happens during the negative alternation. Now the negative alternation I'm going to reuse this circuit because I believe this is actually similar. It is simple, and it is the same as the previous one. So now once we do the negative alternation, positive down here, minus up there, current is now going in this direction. This is reverse biased. Now, at this point, the forward voltage doesn't matter. This diode is just going to always behave like it's open. If this diode is behaving as though it's always open during the negative alternation, that means whatever voltage is applied is the same voltage that I get out. It's that same situation that we keep talking about or running into. We have 0 amps because this is open. We get 0 volts dropped across our resistor, and this is open, so I still measure that electromotive force. I still measure that voltage, that desire to want to do work. Now, there's no current flowing through it, so it's not doing any work, but we still are measuring that potential, that electrical potential. So if we have 1 volt, we get 1 volt. If we have 2 volts, we get 2 volts. Once we get back to the positive alternation, it's just as we did before. You go up to 0.7 volts and you stay there. Okay, so that's the shunt diode clipper. Let's answer the question of whether it's negative or positive clipping. What are we losing here? Well, it looks like we're retaining our negative portion just fine. It looks like we're clipping the top. Even though we're not fully clipping it, we're stopping at 0.7 volts. We still are losing the bulk of the top. So definitely anytime we see a flat line in a waveform, something's getting clipped. So we will go ahead and refer to this as positive clipping, hence, or because we are losing the positive portion of our waveform. Okay. There is one more case. This is still a shunt diode clipper circuit. However, we're going to flip the diode. Okay. So this is the shunt diode clipper. It's the same as before. The diode is still in parallel with V out. However, we now flip this around. So you can see that now that behavior is going to be very similar to the previous circuit, except it just changes which direction that happens. I'm not going to solve this one. I went through 3 of these circuits. I'm going to leave this last one for you. It's part of the lab. You'll see in LT Spice when you model the circuit, you'll see how that's done, and also you can practice this one on your own. All 4 variations of this circuit do come up on the exam. Do we have to remember the names and associate them to the circuit? Yes. Yeah, I may ask. I may ask something along the lines of what's being clipped. So you would want to remember. And the thing is, There's only two things you got to remember as far as the circuit's concerned, as far as the name is. Whether it's a shunt or series and what's being clipped, right? And both of those two are answered in the circuit itself. So don't just remember it. Make it a part of what it is. So over here, is that shunt or series? Well, it's a shunt. This is in parallel with V out, and shunt means parallel. Okay? Okay. Is it negative or positive clipping? Look at the waveform. Solve what V out is equal to. Look at the waveform. Did you lose the positive or the negative? If you lost the positive, this is a positive clipping circuit. And if you lost the negative, it's a negative clipping circuit. So as far as remembering, I don't remember these things. I look at the circuit and I ask myself a couple of questions and I analyze it. Okay? So better to learn the process and the tool than it is to just memorize the waveform and the name. Okay, so I'm going to leave that as that. We will take a 10-minute break. We will come back to lab at 9:10. And this is going to be simulation based. So if you want to go ahead and get started, let me pull up the lab. No, I wanted not chromium, I wanted chrome. I'd also like to ditch that
Okay,
camera.
4, you're just talking about the shunt and series?
Yeah. There we go. Okay, go to 311. Okay, a couple of things I added. I did create a lecture videos tab. However, I'm having issues with YouTube, as I mentioned in an email, so I will be uploading to Beachboard. Beachboard will end up being more to date. Usually that gets it by I think Tuesday, or let's see, we meet Monday, Wednesday. So I think Monday's lecture I posted last night. I'm getting swamped with emails. No joke. I'm up till like 10 o'clock going through emails. And so I forgot to post the lecture video until somebody mentioned it to me. So I have a tab here, and I am putting YouTube links for the videos on the website just so that I can organize and get those eventually. But YouTube, it takes like a day to process the video because they are kind of long, and YouTube doesn't really like, hour and a half long videos. So Beachboard should end up being more to date, but I will also try to keep this on the website. And let's go ahead and look at the lab just quickly. Okay, we did the LED. We are now on Lab 1, Part 2, which is diodes, rectifier, simulation. This is to be done individually. And walk through this. So there is some let's see. Actually, this starts off with simulation. And then it goes into analyzing it by hand. So the idea is you simulate it first, you have what the correct answer should be, and then you do it by hand and you look at that, compare the two, and find out if your theoretical board work using the second approximation, how close does that come to the LT Spice model simulation? Okay, once we're done with this lab, with part 2, we'll actually be constructing this, and I'll be using my oscilloscope on my bench in order to showcase all of these different circuits. Okay, question, do we have to, for lab 1 part 2, do we need to SS all those schematics? Screenshot all those schematics. Okay, lab due, I'm gonna have to think about it and then post that on the website. More than likely it'll be due next next class. Yeah, because next class we're gonna do the oscilloscope stuff. This is due next class. Okay, so let me. This will be due the following beginning of. Let's see. Today's Wednesday, right? So that actually gives you the weekend. That's plenty of time to do this. Okay, and then once we have that for next lab, it'll make perfect sense because you can reference your lab as I step through the oscilloscope on the bench rectifier diode. I'll go through all 4 of these circuits. Okay, cool. So let's meet back at 9:15. Okay, you're more than welcome to start on this. It is the same process for LT Spice as we did previously, where you place a diode and then you right-click on that diode, pick new diode, and select that one N4001. Okay, I'm gonna go ahead, pause the recording, and I will see you guys back in about 12 minutes.